All right, so uh, today we're going to keep talking about random walks, especially in undirected graphs. So let's see. Um, okay, everything looks okay. Okay. All right, so today we're talking about undirected random walks and trying to analyze them in more detail than we did last time. So what did we do the last few times? Uh, So let's see, we did some discuss introducing random walks and talking about the existence of a stationary distribution, even in directed graphs. Uh, we did this discrepancy, which was sort of an interesting application of random walks. But then last time we were looking at this problem of how to do connectivity in log n space. And the algorithm, it turns out, was very simple. Just randomly walk around for polynomially many steps, see if you get to the place you're looking for. But that introduced these notions like hitting time and cover time, right? Hitting time is the expected number of steps to get from point A to point B. Could be infinite if you can't get from point A to point B. And somehow to analyze this, we took this very interesting detour through electrical networks, which is this actually relatively simple optimization problem of sum of squares. And we kind of worked out what are some of the implications of this optimization problem, outcomes, things like Ohm's law and stuff like that. And then somehow we're able to connect that back to the original problem of kind of analyzing hitting times, and via some kind of analogy with electrical networks, partly because they're sort of very similar linear systems uh, underneath it all, we're ultimately able to show that, okay, a polynomial number of steps is what you expect to actually traverse the whole graph. All right, so, okay, but several of you asked questions like of the form like, oh, so we kind of proved this worst case bound of mn for the cover time for any graph that's undirected. But I got several questions of the form like, what about specific graphs, or is there a more detailed analysis for this, more detailed analysis for that? What's a type thing like that? So today we'll give maybe a standard a way to to analyze sort of convergence rates and stuff, and give a more detailed analysis. So. And we're still kind of analyzing random walks in general, so I'm not sure if we're actually going to have any new algorithms per se, but we'll keep studying this random walk phenomena, and some of these things will. Next class we'll have a few more algorithms, but we'll need a lot of structural stuff that we pick up in this class. So let me just state our main goal of this lecture. So today we're not going to be interested in the cover time per se, but rather, we know that every random walk has a stationary distribution, and I might start at one particular vertex and then I start walking around randomly and stuff. And over time, I'm hoping to converge to a stationary distribution. The question is how fast and how long does that take? So for undirected graphs, everything today is going to be specific to undirected graphs. So we know that the random walk matrix R has eigenvalues between 1 and -1. 1 corresponds to the stationary distribution. Okay? And let's say that I listed them in descending order, so mu1 is the first eigenvalue of 1, and then it goes mu2 down to mu(n). Okay? So this theorem is saying, okay, let's look at, I start at some initial point distribution x, it could be all on one vertex, and I take k steps of my random walk, right? So I apply R k times. And I say, okay, how different is my distribution after k steps from the stationary distribution? Okay. And we're going to get some sort of bound like 1 minus gamma to the k times something, where gamma is 1 minus the maximum of the second eigenvalue or the smallest eigenvalue, the absolute value thereof. But let me explain. So we know that mu2 through mu(n) are between 1 and -1. What it's saying is that if it's strictly between 1 and -1, so if mu2 is really smaller than 1 and mu(n) is bigger than -1, that's going to give you some gap gamma called the spectral gap. Okay? And the convergence rate is going to completely depend on the spectral gap. right? 1 minus gamma to the k, okay, that's also like e to the negative gamma k, right? So it's going to kind of converge exponentially fast, but it's controlled by this gamma parameter. Okay, so that's in some sense a much more detailed analysis of random walk than we did last time. In particular, this reflects structural properties of R. Last time was sort of a worst case bound. Okay, so I haven't explained that. Delta max will be the maximum degree in the graph. Delta min will be the minimum degree in the graph. So this is at most n or something, so it's not too big a deal, but yeah. Okay. All right, so we're going to have to, we're going to take quite a detour to get to this point. So I wanted to first say at the beginning what our eventual goal of the algorithm is, because we might lose, or of the lecture is, because we might lose track of it here and there. Okay, but we'll try to come back to this by the end of class. Okay, any questions about the statement? Okay, so, all right, so, okay, whatever. So we need a few tools to get us there. And our main tools are going to come from linear algebra. So I'm going to start there. We're not going to talk about random walks for a little time. So maybe as motivation, we can talk about the Laplacian. So, all right, so I introduced the Laplacian of a graph last class. It came up when we were discussing electrical networks. I'm going to reintroduce it from a slightly different perspective without as much emphasis on electrical networks. Okay, but what's the basic idea? The Laplacian is taking an undirected graph and it's encoding it in some kind of n by n symmetric positive semi-definite matrix. I'll define those momentarily. Okay, and the high level idea is, okay, well, two things going on. One is this is going to encode literally all the information in here. Okay, so given this, you should be able to figure out all the edges and all the edge weights of the original graph. But the high level kind of theme, and we'll explore it a little bit this time, we'll explore it more next time, is that analyzing this linear algebraic object, and in particular looking at eigenvalues, is a big theme. And sort of leveraging the tools of linear algebra, right? We have these very strong tools, right? All these very nice ideas that have already been developed can actually tell us interesting things about the graph that otherwise are hard to see directly. Okay, so it's kind of very interesting because at least, my experience when I, first take algorithms and stuff, everything in graphs is like everything I can just visualize and see very easily. It's combinatorial, everything clicks, it's very simple, right? And then some of these things where we're leveraging, linear algebra or other mathematical things, they're less direct to me, at least, right? Because I have to do something on paper and then try to understand and interpret what's going on in the graph, right? So that's a little bit unusual for me. But on the other hand, we get results that are just so very hard to just see, right? You get, in some sense, less intuitive results, but less intuitive results are often more useful because the other stuff we can more or less take for granted. Okay. All right, so let me define the Laplacian all over again. But first, I need a little bit of notation. Okay, so rank one matrix. This is sort of the simplest kind of matrix. Okay, so the notation I like to use. Okay, you have two vectors u and v. Is this u outer product v? But that's really the same as u v transpose. Okay, so a functional definition is that if I applied x and y to the outer product of u and v, you would just get these two inner products multiplied with each other. That would be the same if you had written uv transpose. Okay, okay, so, and as a matrix, it'll kind of look like this. All right, so all that really matters is rank is some kind of measure of complexity of a matrix. This is sort of the simplest kind of matrix you can get. Okay. So before defining the Laplacian of a graph, I can define the Laplacian of an edge as a simple rank one matrix. Okay. So L sub E will correspond to this Laplacian of a single edge. It's the outer product of sort of the indicator variable for U minus the indicator variable for V. So that means you have some big vector indexed by all the vertices. U will have a 1, V will have a -1, everywhere else is 0. Okay, and it's sort of the outer product of this thing. Okay, We could have defined it 1v minus 1u as long as both sides are the same, because I was sort of putting a negative sign on each side, so they sort of cancel out. No big deal. But maybe a more functional definition to keep in mind is just if I apply this to x, okay, all it's doing is it's looking at the endpoints of the edge and the values at the endpoints, and then taking the sum of differences squared. Okay, that's what L sub E does. Okay, fine. And then finally, we can define the Laplacian of a graph as the weighted sum of these individual edges. Okay, edgewise Laplacians. That means if I'm applying x, I'm kind of doing an inner product over L, so to speak, xLx. Then I'm summing over all the edges, and maybe it's weighted by the edge weights, but just taking the difference of the endpoints squared. Okay, so you just have all these kind of potentials on all the vertices of your graph, and you're going through all the edges and looking at the different squaring, looking at different squaring, looking at different squaring. Okay, so that actually came up last class where if x were actually the potentials of the electrical flow, okay, and the weight was 1 over the resistance, this is actually giving you the electrical energy of the flow. Okay. All right, so I'm really using, though, for this class, the Laplacian as an example of a positive semi-definite matrix, which is a very nice subclass of matrices. Okay, so a matrix is positive semi-definite if it's symmetric, and if xax is always greater than or equal to 0. Okay, all right. I'm claiming the Laplacian is symmetric, but why? Well, okay, so at some level, if we look at just the Laplacian of a single edge E, which is 1 minus u, the kind of the outer product, that's clearly symmetric. And it's just a sum of these symmetric terms. So a sum of symmetric matrices is symmetric. Okay, the other one, the claim is that xax is always greater than or equal to 0. That's the other thing we need for a positive semi-definite matrix. Why is that true of the Laplacian? It's a sum of squares. Okay, and sum of squares is always non-negative. Okay, the edge weights here are non-negative. Okay. And that's all we know, and yet this reveals quite a lot of structure. Okay, so, all right, so if you remember from, I don't know, probably a couple of weeks ago, the eigenvalues are vectors that sort of go into x and come out in the same direction. So ax is equal to lambda x for some scalar lambda. So x may stretch, it may become negative x, but the point is you're still roughly in the same, or still in the same dimension of x. Okay, so what goes into A comes out same direction. And we also showed that every linear map will always have a complex valued eigenvalue, right? And complex valued eigenvector. Although often complex valued things aren't really so useful for us. Okay. So for random walks, we could appeal to this Perron-Frobenius theorem, and that asserts there's a real valued eigenvalue, which is unique. Which is a very special case. And we're going to try to do something similar for symmetric matrices, where we can leverage the symmetry to try to get something stronger than just a complex valued eigenvalue. So here then is the claim. So if you have any symmetric matrix, consider this optimization problem where I'm trying to maximize xlx over all unit vectors x. Okay. We could have also done with min, but here we're going to do max. Okay. So this x that's just trying to maximize sort of simple expression is always going to be an eigenvector. Okay. And not only that, but mu is going to be equal to that optimum value of this optimization problem. Okay. And since x is real valued and L had real coefficients, XLX is also real valued. So mu will be a real valued eigenvalue. Okay. So what's kind of nice about this, and maybe even nicer than Frobenius. Okay, so first you do get this real valued eigenvalue, real valued eigenvector, which is great. If you didn't have that, we would be in a world of hurt. Okay, so that's maybe we take it for granted, but it's very nice. But one thing cool about the symmetric case is just how transparent it is to get one eigenvector, right? X is simply maximizing this relatively simple problem defined by L. So you can kind of see one way to extract an eigenvector. That's more transparent than Frobenius, which was a bit of a complicated proof or construction. Okay, so, all right, so this is what we're going to prove. This will probably be the most kind of mathematical portion of the class. Okay, so let's prove this thing. Okay, so what we're going to do is we're going to break it. Instead, we're going to focus on this claim. I'm going to read this claim aloud and then see why it implies the rest, and then we can focus on the claim. All right, the claim is that for any vector u that's orthogonal to x, so u dot product x is 0, u is also orthogonal to Lx. Okay. So any vector that's orthogonal to u is orthogonal to Lx. That's the claim. Any vector u that's orthogonal to x is orthogonal to Lx. That's the claim. Okay. All right. And now I want to suggest that if that claim was true, then the rest of the lemma will follow. Let's see. Maybe I can suggest. Okay. So I guess it's hard to guess the first step, but it's more interesting to ask why the first step is true. Okay. The claim is that if the claim is true, then Lx must be spanned by x. That is, Lx is in the, is some multiple of x. Okay. All right. But why? Yeah, but expand that like a little more. What is u? Yeah. Well, for example, if we're in 3 dimensions, uh, here's 3 dimensions, okay? And let's say here's u, and then here's x, and then here's Lx. They're all mutually orthogonal, but Lx is not in the same direction as x, right? Okay, so the quantifier is important. So actually it's for all u. So if this is orthogonal to x, then this is also orthogonal to x, and this is orthogonal to x, and any other, this is orthogonal to x, and this is orthogonal to x. So that means this is also orthogonal to Lx, that is also orthogonal to Lx, and all that's left is that first direction of x. Okay, so what's happening is that all the dimensions orthogonal to x are orthogonal to Lx. So Lx must live in the one dimension left of x. If we wanted to do it slowly, we could start with x and expand it out to an orthonormal basis of the entire space. And we'll see that Lx has to have sort of 0 component in all the other ones and can only have non-zero. Okay. All right. So if Lx is in the span of x, does that finish our theorem? Our theorem? If so, why? Yeah, okay, so that means that Lx must be of the form mu x for some mu. Okay. And now, what about the value of mu? Yeah, okay. So also keeping in mind that x was a unit vector. All right, so mu times, so x is 1, because x is a unit vector, and then that just, the mu x, one of the mu x's become an Lx. Okay, so everything kind of works out nicely once we have the claim. Okay, so the real grungy part is this claim. Okay, so we want to show that if if u is orthogonal to x, then u is also orthogonal to Lx. Okay, so to this end, we're going to do some calculus and that'll prove it. There's different ways to prove it, but let's let u be orthogonal to x and also have unit length. Okay, and let me define this function f of epsilon, which is x of epsilon mu. Okay, but what's this really doing? Okay, so at some level we're taking x and we're adding epsilon u. Okay, now one thing to point out is that the length of this epsilon u, x plus epsilon u, because u and x are orthogonal to each other, it expands out to x squared plus epsilon squared u squared. Okay, so really there should be an inner product here, like epsilon times x dot product u, but that dot product is 0 because x and u are orthogonal. Okay, so that drops out, and these are both unit vectors, so it's 1 plus epsilon squared. Okay, so what you could think of what this denominator is doing is sort of renormalizing the x plus epsilon u arguments. Okay, so it's really taking two unit vectors, which is x plus epsilon u, over square root of 1 plus epsilon squared, and applying it to L. Okay, that implies in particular, what is the maximum of this function? Well, what value of epsilon maximizes f? Uh, no, so there's a more direct way to try to figure out what value of epsilon will maximize f. 0. Why 0? Uh, yeah, so okay, so x maximizes xlx over unit vectors. And again, x plus epsilon u divided by square root of 1 plus epsilon squared, that's a unit vector. Okay, so this is actually also doing a sort of xlx over a unit vector x. Okay. All right, so f is maxed out at epsilon is equal to 0. So we won't do the entire proof. You'll see why I get lazy. So that implies that f prime of 0 must be equal to 0. Right? Simple enough. And this is the part that I relegated to an exercise, but it'll take not too long, but I don't know if you guys would want me to do this. You work out what this would be. Okay. And then you plug in f prime of 0 is equal to 0. And that'll tell you out from inside will come out that ulx has to be equal to 0. Okay, we can do it, but yeah. Okay, but anyway, we look at the first order conditions of this. All right, good. I'll just leave it at that. Okay, so that would prove the claim, and then everything else would follow. Okay, but I think maybe the high level takeaway is that, or maybe it's good to keep in mind that we're analyzing some matrix L. We don't know very much about L. We just know it's symmetric, right? But it turns out that's enough not only to assert that there's real valued eigenvectors and eigenvalues, but there's sort of an explicit way to get it. You can maximize xlx over unit vectors, right? That's very strong. especially considering how little we knew about L. Okay. All right, so it's going to lead to this theorem, which is even stronger. It's called the spectral theorem for symmetric matrices. Okay. All right, so we just showed how to get one eigenvalue and one eigenvector, right? But now look at this. This claims that if L is symmetric, okay, all I know about the matrix is symmetric. Otherwise, you can have any numbers you want, positive, negative. Okay, just has to be the same across the diagonal. L can be written as a sum of rank 1 terms, sum of n rank 1 terms if it's in n dimensions. So lambda 1 times v1, the outer product of v1 with itself, up down to the nth eigen lambda n, and the outer product of vn by itself, where all of these lambdas are real valued. And then here's the kicker. v1 through vn form an orthonormal basis of Rn. Okay? So just by virtue of L being symmetric, again, this is very little information, you can actually break down L into this outer product of like an orthonormal basis. Okay. All right. So even before worrying about the proof, what does that tell you about the eigenvalues of L? So all you know about L is that it has this form, which maybe you're looking at and you're saying, oh, doesn't that look bigger than L? Maybe that doesn't look simpler, but this question will make it more clear. So you know that L has this form. What do you know about the eigenvalues of L? Yeah. They are real. And what are the eigenvectors? Yes. Yes. Okay. But okay. What are the eigenvectors? The V1 through Vn. Okay. In particular. So if we plug in any L, let me get a different color. If we plug in some LVI, okay, then we get this sum of lambda I. Oh, that's bad. If I plug in some LVK, okay, and we break it down like that, okay, and what happens is that only the rank 1 terms with K, okay, so the next step would be, okay, because that's what the rank 1 term does. It's going very slowly. And because it's orthonormal, if I is not equal to K, this becomes 0. If I is equal to K, it becomes 1. Okay? So all you're left with is lambda K VK. Okay? So you have this orthonormal basis of eigenvectors of L with real valued eigenvalues. Okay, that's tremendous. By the end of this lecture, we'll see quite how useful it is, because that's really what's going to let us analyze random walks and get that very sharp bound from earlier. Okay, but I really cannot understate how wonderful it is to have the structural theorem about symmetric matrices. Yeah.
Just checking. DK is just one of those.
Oh yeah, K is some index between 1 and n. Yeah. Okay. All right. Okay, so how do we prove this? You guys might be able to guess or suggest reasonable ideas. So we want to decompose L into this sum of orthonormal eigenvectors, outer products of orthonormal eigenvectors. Yeah. Okay. Okay. Good. Okay, let's try to follow your instructions exactly. So I'm going to actually do it from lambda n, but it doesn't really matter too much. So let's let all right, so let Vn maximize Vn LVn subject to Vn having unit length, right? And I'm going to let lambda n be the corresponding maximum value. Okay. All right. So, okay. So that makes sense. That's how we'll actually get our nth one. Okay. Um, good. But now how do I, okay, so you may have said it already, but so I'm just, this might be redundant. Okay, so now how do I sort of proceed next, I guess, or what's the one way to proceed? Yeah, or maybe you said it. What did you say? Okay, B is equal to A, let's say, okay, minus, I guess it could be an A. All right, okay, so, okay, so first of all, A is symmetric, right? That we can see because we took a symmetric thing, we subtracted another symmetric thing. So we know it's symmetric. Okay. All right. Okay. Okay, good. So we have this matrix A, right? But maybe one thing worth pointing out is that A is still living in Rn by Rn, right? So at some level, I can't just like, it would be nice if I can just like, oh, by induction recurse on A or something, right? But I haven't really decreased anything to induct on. I would just get like another n vectors for A, and now I have n plus 1, including the first one I just found, right? Okay, so this is the only part that maybe requires a little bit more care and expanding out on, although this is the right first step to subtract it out, okay? So maybe one thing to point out is, okay, what is AVN? AVN is 0, because this will be LVN minus lambda NVN. Um, okay, then what's one way to prove this? Uh, okay, so that's fine. Oh, no, no, sorry. I'm being silly. We've already established at this point that Vn is the eigenvector with eigenvalue lambda, so okay. This we know from our previous lemma. Okay, good. All right, so fine. Now let me define a subspace Y to be the set of vectors orthogonal to Vn. Probably implicitly in your mind, when you said let's subtract out Vn and sort of recurse on the rest, you're also kind of thinking let's subtract out Vn from the vector space and sort of work in the space orthogonal to Vn. That's what we're going to try to do. The only thing we need to sort of verify before we can do that is to show that A maps Y into Y. Okay. So it would be nice to recurse on A inside Y, but we need to justify that A sort of lives in Y, so to speak. Okay. Um, okay, so let's just do this then. I'll let you guys, I'll let you guys shout out the derivation. Okay, so I want to show that AY is in Y. Okay, so that means I want to show that XAY is somehow equal to 0, right? I want to show that AY is orthogonal, not X, is orthogonal to Vn. Okay. All right, so fine. Anyone want to take a stab at this? How do I, yeah. Ah, okay, good. This is the only thing we ever do, it seems. Okay, we take the transpose to the other side. In this case, it's symmetric. Okay, and then, okay, we just showed that this is the 0 vector, and that's equal to 0. Okay, all right. So A maps Y into Y. Okay, so at some level, I can sort of look at A restricted, as a map from Y to Y. Okay, inside Y, it's still a symmetric linear map. Okay, but Y now officially has one dimension less than the original space. Now I can properly do my induction argument. Okay, so by induction, then we have that A is equal to some orthonormal outer product of orthonormal basis. Uh, Sorry, there's so much writing to do. Okay. All right, so by induction, now on the dimension, we can properly do this. Okay. And now our original thing follows, right? Now we just throw lambda in back in and we're done. One thing nice is we already know that Vn is orthogonal to all of these because these are coming from the subspace Y of things orthogonal to Vn. That's the only thing to check. Okay, so that's it. Okay. But roughly, the first lemma lets us peel off one eigenvector, and we can do induction with a little bit of care. Okay, good. I think we're out of the woods mathematically. All right, so good. So we have this very nice spectral theorem that will break down any symmetric matrix to us into these sort of n-principal directions. These are eigenvectors, right? And so let me give an example. So for any vector in Rn, I can write vector x in Rn. I can write x uniquely in terms of this basis v1 through vn, right? X is some alpha 1 v1 plus alpha n vn. And of course, each alpha I is equal to the inner product of x and vi, right? But this is just a change of coordinates from the original basis on Rn to the basis given by v1 through vn, right? Okay, so let's see what Lx does sort of to these coefficients alpha, right? So, okay, I didn't do anything here. I just wrote out what's going on. But what this is giving us is lambda 1, alpha 1, right? Because v1 x is equal to alpha 1. v1 plus lambda 2, alpha 2, v2 plus lambda n, alpha n, vn. Okay? All right, but, okay, so look at if I take these parts that I'm underlining, right? This is the original x in that other coordinate basis, right? Alpha v and alpha 2, so forth. And so what you see L doing is it's sort of working in this axis, right? It's sort of working in this the basis given by v1 to vn, and it's just stretching out each of the coordinates. It stretches out the first coordinate by lambda 1. It stretches out the second coordinate by lambda 2. It stretches out the nth coordinate by lambda n. Okay? What does that mean? That means L up to rotation, up to some change in basis, is a diagonal matrix. Okay? So what we've shown, so diagonal matrices are the nicest things in the world, right? Like if we're only working with diagonal matrices, you don't really need any linear algebra because there's no ever interaction across dimensions and rows and stuff, right? So diagonal matrices are the world's easiest thing to work with. And this is saying that every symmetric matrix is the world's easiest matrix. Okay, it is a diagonal matrix. The only thing is that it's in some basis that's sort of unknown unless you do some optimization, you figure out what the basis is, right? So there's some change of coordinates, but if you can look at L the right way, it's fundamentally very simple. It's fundamentally a diagonal matrix that's just stretching out each of the coordinates. Okay, so it's very strong. Again, all we're using is the fact that L is symmetric, and now comes a lot of structure. Because you used to think of like matrix as almost like the movie Matrix, with just random numbers streaming down, right? So we've kind of gone from random numbers streaming down to a huge amount of symmetry. Okay. All right. Okay. So that was the first part, just establishing the spectral theorem. Okay. Now let's figure out how to apply it to random walks and see if I can convince you that it is useful. We might finish early today. It's never happened. Okay. All right. All right. So remember last time, or last time before last time before last time, when we talked about page rank and we talked about the existence of a stationary distribution, right? Okay. So there's something with eigenvalue 1. All right. So compare that now to this theorem, which only holds for undirected graphs. Okay, so last time we did directed graphs, that's more general. So we already know there exists some stationary distribution in undirected graphs, since an undirected graph is a directed graph. Okay, but not only does an undirected graph always have a stationary distribution, but I can tell you exactly what the stationary distribution is. So I'm letting S denote the stationary distribution. And this is saying that the stationary distribution is proportional to the degrees of the vertices. Okay? The stationary distribution is proportional to the degrees of the vertices. So the numerator is the degree of a vertex, and the denominator is 2 times the total sum of the edge weights, which is really the total sum of all the degrees. So this again is a very strong statement. You take any undirected graph, it may seem really, really complicated. You ask what seems to be a difficult question: what is the stationary distribution of this big undirected graph? And it turns out there's nothing to it. It's just something proportional to the weighted degrees of all the vertices. Okay. All right. So this is not so tough to prove. Is it guessable? Let me see if it's guessable. Maybe not. Well, okay. By the way, I'm also assuming the graph is connected, in which case everything is unique. Okay. All right. So, well, okay. So here I'm going to let D and RV be the degrees. Okay. And that'll be true for the rest of the lecture. So I'll just use D as a vector that represents all the degrees. Okay. All right. Okay. So, and I'm going to let D, capital D, be the diagonal vector. Okay. All right. So if you guys remember, we can write R as AD minus 1, where A is the adjacency matrix. So this is just putting the weights of the edges. Okay, and what the D minus 1 does is just divide, because you choose one of the edges uniformly at random when you take a step. Okay. So to figure out to sort of test if something is a stationary distribution, so to test if something proportional to D is a stationary distribution, I just need to check to see if D is an eigenvector of eigenvalue 1. There's only one eigenvector of eigenvalue 1 was all positive by Perlin-Frobenius. Okay, so R D is equal to A D minus 1D, right? And then what's D minus 1D? All ones vector. And then what's applying the all ones A to the all ones vector? So it should be a vector that comes out. So it can't be A if you said A. D. Okay, because each row corresponds to all the edges incident to that vertex, and you're just applying all ones. Okay. All right. So RD is equal to D. So D is an eigenvector of eigenvalue 1. The stationary distribution is proportional to D. Okay. All right. Okay. Simple enough. Not a very complicated proof. Maybe I should point out though that one reason why we have such a simple proof, I only have to check that D is an eigenvector of R with eigenvalue 1, is because we built up all this machinery to reduce it to that point. At some level, we are proving something rather sophisticated where we get exactly the stationary distribution, but with Perlin-Frobenius and all this stuff we've built up, it's now fairly easy. Okay, all right, so now we're getting a little bit closer to this thing we really want to prove. Okay, so we know what the stationary distribution looks like. Now the next question is, how long does it take for a random walk from some vector x, any vector x, or any initial distribution x to converge to the stationary distribution? Okay. All right. So I need to introduce some terminology. So what we want to do at a high level is I want to apply the spectral theorem that we worked up before to the random walk matrix. But the random walk matrix is not symmetric. Okay, so R is equal to AD minus 1. That's not a symmetric matrix. Okay, but we're going to show that it's similar to a symmetric matrix, and then we're going to be able to extract a lot of structure. So the definition of similarity: two matrices A and B are similar if we can write A as C minus 1 BC for some invertible map C. So for example, C could be a change of basis, right? In which case it's sort of saying, okay, A and B are sort of the same except for a change of basis. Now C is not necessarily a change of basis, it's more generally an invertible map, but in general, you're hoping that invertible maps, isomorphisms, things that go back and forth, right, bijections, roughly preserve information. What goes in is exactly what goes out. So in some sense, you're hoping that A and B have the same information. Okay, but we'll start with something small. C maps, so the kernel of A with vectors that AX is equal to 0. Okay, the claim is that C maps the kernel of A to the kernel of B and vice versa. And I think there's very little to this beyond just double checking. So if AX is equal to 0, okay, and then if I look at B, I want to show that this is equal to 0, right? Because that means C is mapping something from the kernel of A to the kernel of B, okay? All right, so I guess what would I do here? Yeah, okay, so what would I plug in? Okay, so that means BC is equal to CA if I put 1C on the other side. X, and then we get C0, which is 0, okay? And I think if we did the other direction, we get the same thing. Okay, so no big deal. All right, so but why is this more interesting? I'm really interested in eigenvalues and eigenvectors. So what I'm really interested in is if A is similar to B via this isomorphism C, okay, then A and B have the same eigenvalues, and not only that, but C will map eigenvectors of A to eigenvectors of B. Okay. Okay, so this is at some level going to be a very useful tool for us because at some level, let's say that A is difficult to deal with, but B we know everything about, and we know some connection between A and B via C. then actually we know everything about A. So it's sort of a connector. Okay, so why is this true? What's a short proof? I'm not sure if this is guessable. Yeah. Yeah, okay, so I'll do a trick proof and then I'll do your more direct way. So one trick proof is that for all lambda, uh, if I compare A minus lambda I and B minus lambda I, so we can think of the eigenvectors corresponding to lambda as vectors that are in the kernel of this thing where I'm subtracting out lambda, right? And I would have something like this. Okay, and I just showed that we preserve kernels, so that means it's going to preserve the eigenvectors for that lambda, and I can apply that to all lambdas. I guess the other thing is the more less slick version maybe is that if ax is equal to lambda x for some x in lambda, then we could probably figure out some way to make this work. So if we looked at if I looked at bcx, then we can write like, oh, this is c minus 1 bcx, which is cax, which will give us our lambda cx. Okay, so C will map an eigenvector of A to an eigenvector of B. Maybe that's easier. Okay. All right. Okay. But okay, what's really going on is that similar matrices have matching eigenvalues and eigenvectors. Let's put that to use now. All right, so again, the primary difficulty of dealing with a random walk matrix at the moment is that it wasn't symmetric, whereas a symmetric matrix, we know a lot about it. Okay. So what we're going to do is we're going to look at something that basically takes R and tries to make it symmetric. So we'll call it the normalized random walk. Let's let Q be equal to D minus 1 half R D 1 half, which if I expand out, R is equal to AD minus 1, gives you D minus 1 half AD minus 1 half. Okay. All right, fine. Nothing big. It's just some algebra. So what are some interesting properties about Q? What sticks out to you guys? Don't be shy. Okay. Q is similar to R. So Q will have the same eigenvalues and we can map eigenvectors from one to the other. Okay, so analyzing Q will reveal hopefully a lot about R. Okay, and then what else is nice about Q? There's one more thing. It's symmetric. So if we look at that second equality, D to the minus 1 half A D to the minus 1 half. So the two D's, that's symmetric parts, right? Because it's diagonal and it flips over when you take transpose. What about A? Why is asymmetric? It's an undirected graph and it's the adjacency matrix. So if there's edge from A to B, there's edge from B to A. So A is also symmetric. So Q is a symmetric matrix, which is similar to R, okay, and has the same eigenvalues. Okay. All right, so we can write all right, so we can write Q, okay, as some kind of eigen decomposition. So I'm going to stick to the convention where the mu's, the eigenvalues are listed in decreasing order. So the first one, mu1, is always equal to 1. Why is the first eigenvalue 1? Why is the first eigenvalue of Q equal to 1? The biggest eigenvalue. Perl Frobenius, and the fact that it has the same eigenvalues as R. So that extends immediately to Q. That means the smallest eigenvalue is at least negative 1 as well. Okay. All right. So Q breaks down very nicely in some orthonormal bases, V1 and V2 and sort of Vn. Okay. All right. Well, okay. All right. We can figure out what V1 looks like. Okay. How do I figure out exactly what V1 is? Yeah. And what is, okay, so we should map to an the eigenvector corresponding to eigenvalue 1 for R. And what's that eigenvector called? What's the first eigenvector for R, or the one corresponding to eigenvalue 1? It's a stationary distribution. All right, so du to the 1 half V1 should map to, should be something proportional to the stationary distribution, right? Okay, so that means that, okay, so at some level, V1 is proportional. I don't know if this, sometimes I see this symbol, is proportional to d to the minus 1 half times the stationary distribution, which is proportional to the degrees d. Okay. So I'm going to sort of make up some notation, and I'll call this square root d, which is just the vector d except all the entries are the square root. So the vth coordinate is the square root of the degree of v. Okay. The other thing I know about v1 is that it's normalized. Okay. So that means v1 should be equal to square root of d, or the square root vector of square roots, divided by the L2 norm of d, just to normalize the vector. Okay. Now, this squared, which is inner product of square root d with itself, okay? So then you roughly get rid of the square roots, and you would get the sum of degrees, right? So, oh, Jesus. Okay, you would get something like the sum of degrees. Okay. So that tells us that V1 is exactly square root of d divided by the square root of the sum of all the degrees, which is also equal to 2 times the total weight of all the edges. Okay. All right. Okay, so we're learning quite a lot about V1. So if I plug in what we just did, square root d divided by square root of 1 inner product d, plus the outer product, so the two square roots cancel out. Okay. We now know that the normalized random walk matrix looks exactly like this. We even know what the first eigenvector looks like. Okay. All right. Okay. So we're going to use that to try to prove this theorem, which is the whole point of our discussion. Okay. All right. Okay. So let's see. If I look at this, right, then we also get R is equal to d to the 1 half q d to the minus 1 half just by flipping those d's around, right? So we're going to use that to analyze this. So I want to analyze what happens when I apply r k times to a vector x. Okay. Now, okay. So this simplifies to, and I'll let you guys explain to me why, d to the 1 half q to the k, d to the minus 1 half x. So the k has sort of gone on inside and only gone around the q. So what happened to all those other d to the 1 halves? Yeah. Okay, so you annihilate it, right? So when d to the 1 half, q, d to the negative 1 half, d to the 1 half, q, d to the negative 1 half, In the middle, we had a d to the minus 1/2 times d to the 1/2, and they annihilate each other. Okay. All right, great. So that's already kind of like a little bit cleaner. And we can plug in this big thing. Rats. Okay, there's a way to make this big thing a smaller thing. Okay. This is roughly what we do in papers, right? When we run out of space, we just make the margin smaller and the font smaller. Okay. All right. I'm missing a K. All right. Okay, good. I want to simplify this middle term. I want to take the K on the outside and bring it inside. Does anyone want to guess what we can do next? Otherwise, I'll do the thing where I. Yeah, okay. Yeah, so imagine even if K is just 2, right? And if I had these two big sums and they're multiplying each other, I'll get like V1 times V1 outer product V1 times V2 outer product V2 in terms like that, these cross terms. Now they'll go to 0 because in the middle you get an inner product between V1 and V2. Okay, so the cross terms all disappear. No, let me undo that. So we can immediately just bring the K inside. This one's a little bit annoying. I'll do a different color. Okay, so this is to the K. Oh no, one sec. Let me even expand more. Okay, so not only do the inner products disappear, I mean the cross terms disappear, but even the V2, let's say the same ones, it's like V2 outer product V2 times V2 outer product V2. That just gives you V2 V2 again. Okay, so let me explain. So if you had VI, okay, so in general, VI outer product VI times VJ outer product VJ is going to be equal to VI inner product VJ VI outer product VJ, just from some definitions. Okay, so if I is not equal to J, this is 0. If I is equal to J, it's also equal to 1. Okay, that's the other point I wanted to make. So now, when I'm bringing the K inside the parentheses, I'm actually only applying the K to the mu's, to the eigenvalues. There's no, yeah. In other words, V2 outer product V2 to the K is just V2 outer product V2. Okay. All right. Okay, so, okay. Now what I want to do is I want to kind of break off this from the rest. Okay, so I'll do it slowly. So I have one term that looks like d to the 1/2 square root d outer product square root d over, and I have another term that looks like all of these. Why do we, sorry? Okay, so the first term was although it's now written in a different form, it's still V1 outer product V1. So it's still two, and so you still have the same to the K disappearing. Okay, so that's actually a normal vectors in disguise. Okay. D to the 1/2. Sorry. The only thing about this is that there's a lot of writing. It's painful for you and for me. Okay. Now if I look at this part here, I can bring the D's in and make this a little bit simpler. Okay, so D to the 1/2 Okay. We can actually apply the d's to each of these. And so you'll get something like d like that. Okay. And if I applied x to it, okay, and x, all I know about x is some distribution I started with. Okay. So then we would get d over 1's d times the inner product of 1's and x. And I know that this thing sums to 1. Okay. And then what is this term? This is our stationary distribution. Okay. So that means if I went all the way back, we're left with the stationary distribution plus something like this. Okay. So let me zoom all the way back. We asked what happens when I apply k steps of the random walk to this initial distribution x. You get the stationary distribution plus some leftover terms. Okay. We want to argue that these leftover terms are relatively small, as long as all the values mu2 through mu(n) are like, say, well within the range, -1 and 1. Let's say everything is between -1/2 and 1/2. Or, yeah, -1/2 and 1/2, right? So very far away from the extremes. Then what's kind of going on in here? This is going down really, 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 really fast. Okay, so in other words, we sort of have one direction corresponding to the stationary distribution that just fixed. And these are all the other orthogonal directions. Okay, and the orthogonal directions are just dwindling. And you're going to be, most of the mass is going to be left on the stationary distribution. Okay, so to formalize this, if I wanted to look at RKX minus the stationary distribution, and I wanted to measure the L2 norm squared, okay, then you're looking at this kind of crazy thing. Okay. All right. So what's worth pointing out? So we also know from the spectral theorem, right, that, well, this applies in general, but if okay, is this really necessary? Okay, so let's look at this. So what this is going to do is it's going to first calculate this, and then take some weighted sum times the degrees. Okay, so I can get rid of this, and the effect of the d to the 1/2 is to increase the overall thing by at most the maximum degree. Okay. So now we have this term. Okay, maybe we won't finish early after all, but we'll finish on time. Okay. All right. So let's see what to do next. Okay, I'm going to call this S. Okay. So if I look at S, d to the minus 1/2 x, I could think of it as applying, okay. All right, so just expanding out what the inner product is, there's an s squared in the middle, right? Okay, now my next goal is to get rid of the s2 term, okay? Maybe what I'll do is I'll write the next step and ask you guys to justify it. Okay, so why is this true? Why was I able to, at some level, get rid of the s squared term and replace it with some kind of maximum over the eigenvalues, the absolute eigenvalues? Yes, and? Yeah, okay, so we showed that xlx is less than equal to whatever is the maximum eigenvalue of L, right? If x was normalized. If x wasn't normalized, then it would be like this, which is just throwing the normalization on the other side. Okay, so what is the maximum eigenvalue of s squared? What are the eigenvalues of s squared? It's going to be mu2. In fact, I got some of this wrong. So this should be mu2 to the 2k, mu n to the 2k, right? So the only reason we put the absolute value there is if, mu n is really close to -1, then the squared might suddenly become the biggest eigenvalue of s. Okay. All right. So that's good. Make that disappear somehow. Okay. So this is our spectral gap, 1 minus gamma uh, to the k, where gamma was, yeah, okay. All right. And then finally, d to the minus 1/2 x is going to be dividing, this is some, if I expand this out, this will be xv squared divided by the degree v squared, right? So, okay, at the very least, each one is being divided by at least the minimum degree in the graph, xv squared, okay? Somewhere up here, there was a degree max from getting rid of the d 1/2 for the exact same reason. So putting everything together looks a little bit cleaner than the notes than this. Ultimately, we got that this thing, uh, how fast it converts to the stationary distribution is at most, okay, this is 1 minus gamma to the 2k. 1 minus gamma to the 2k delta max over delta min. Okay, it's a little bit crazy, a little bit chaotic, but okay. And that's how we get ultimately our theorem. Okay, so I understand that this part here just seems like, okay, we just have this big thing and we keep applying one thing after another after another. Eventually we get something. But let me just take one step back and try to explain maybe the high level key ideas. So first, keep in mind this is a very strong result, right? I mean, we're getting a very sharp convergence rate. So just because we do it doesn't mean it was easy. Okay. But I think what's going on in the proof, right, is we know that symmetric matrices are diagonal matrices. So we know what powers of diagonal matrices look like, right? Because it just takes all the entries and takes the kth power. Random walk is not a symmetric matrix, but it's similar to a symmetric matrix, okay? Which means it's similar to a diagonal matrix. So powers of the random walk of an undirected graph were easy to analyze, right? It was notationally a bit cumbersome, to carry around this huge sum of outer product terms, but that's really just expressing a diagonal matrix, except having to mention the basis V2 through Vn explicitly. But ultimately, we're just looking at diagonal matrix raised to a power of k. Okay, and so it's for this reason we're able to analyze random walks, which we can't do for directed graphs, because directed graphs doesn't have this connection to symmetric matrices. It doesn't have this connection to diagonal matrices and stuff like that. We can't get sharp bounds. Okay. All right. Then that concludes that, and we'll do something more algorithmic next time, but in connection to what we did today. All right. Thank you.